Hello, my name is Maluja Ashley Hope, and today my colleague and I will be presenting on cache-augmented generation. Um, Cache-augmented generation is a technique that enhances AI models by storing and reusing previously generated responses. Just imagine you ask ChatGPT the same question twice. It would be easier if the second response came instantly instead of being generated again. That's exactly what cache-augmented generation does. It remembers previous answers, and by doing this, reduces processing time and improves efficiency. We're going to explore how it works. We're going to compare it to retrieval-augmented generation and introduce key mathematical concepts and see an example in Python. So, before we can dive into cache-augmented generation, we first need to understand what retrieval-augmented generation is. Imagine you're writing a research paper and need information on different machine learning techniques. Instead of memorizing everything, you Google each concept as you write. This is how retrieval-augmented generation works. It retrieves external information in real time before generating an answer. So, while RAG provides accurate and up-to-date information, it has drawbacks. For example, slower responses. Because it retrieves data in real time, that's going to cause some sort of latency. It could experience errors in retrieval, whereby the model may pull incorrect or irrelevant information. More system complexity, as it requires integration with external databases, which can complexify the model's architecture. So, instead of retrieving new information every time, we can use cache-augmented generation, which stores frequently used responses in cache for faster access. For example, imagine you're a teacher grading students' work. If many students make the same mistake, you don't write the explanation every time. You copy and paste your feedback. That's how cache-augmented generation works. It reuses previously generated responses instead of regenerating them from scratch. This reduces the response time and simplifies the system. So, before we can use cache-augmented generation effectively, we need to pre-process documents to store structured knowledge. For example, if you're preparing for an exam, you don't memorize the entire textbook. You create summaries of flashcards for quick revision. Similarly, cache-augmented generation follows some pre-processing steps. For starters, we break down text into smaller units, which is that's known as tokenization. And then we remove irrelevant details from these small units. And then we structure the data for easy lookup. In other words, we store key points in a format that can be accessed quickly. So, the mathematical representation of preprocessing is seen in this formula that we have here. So the D represents document or data set, and the KV encode this basically converts it into a structured representation for fast retrieval. This ensures relevant knowledge is preloaded into the system, reducing the need for real-time retrieval. So once documents are preprocessed, cache-augmented generation moves to the inference stage, where it decides whether to use cached information or generate a new response. Think of a restaurant. If you order a popular dish, the chef might have it pre-prepared. In other words, that's a cache hit. If you ask a question and cache-augmented generation checks the key value cache, and you asked this question before, then there's a cache hit. But there's a cache hit, and okay, your response will be got from cache and sent to you, so it will be immediate. But if you say, okay, if you've never asked this question before, then of course it's going to take longer because now it needs to be generated from an external database. So instead of retrieving external data, Cache-Augmented Generation loads the pre-computed key value cache alongside the user's query queue, as we can see in our mathematical formula here, where Q is the user's query, CKV is the pre-computed knowledge, and altogether the M into Q/CKV represents the model retrieving knowledge from cache instead of searching for it externally. So to generate a response, the model concatenates the preloaded knowledge with the user's query, which we can see being done using this formula here. This eliminates the need for dynamic retrieval, making responses faster and reducing the computational overload. So, storing responses is great, but what happens when the cache becomes too large or outdated? That's where cache reset strategies come in. For example, think of your phone storage. If you never delete old files, your phone slows down. So either you delete old files manually or let the system auto-delete unused files, which brings us to the cache reset in Cache-Augmented Generation. So instead of wiping everything, Cache-Augmented Generation truncates newly appended tokens to the cache efficiently, as you can see here in this formula, where T1, T2, and TK are the most recent tokens added to the cache. This truncate removes excess data while preserving important knowledge. So, important knowledge. There are cache management systems that we can use, but my colleague will get into those more and explain more on them. Now that we understand the theory behind Cache-Augmented Generation, we're going to see how it works in practice using Python. So this code demonstrates how we can cache AI-generated responses to improve efficiency. And I'm going to walk you through the implementation step by step. So first, we're importing the OpenAI library, which allows us to connect to OpenAI's API and generate text-based responses using large language models like, let's say, GPT-3 or maybe GPT-4. And then here we are creating a simple cache using a Python dictionary. The purpose of this cache is to store previous responses so that if the same query is asked again, we return to the cached response instead of calling OpenAI's API again. So this helps us to reduce latency and saves computational responses. So this function generate text with cache. It takes a user's query or prompt as input and then checks if the response is stored in cache. If the response is not in cache, we generate a new response using OpenAI's model and then store it in the cache and return it. This ensures that we only generate responses when necessary, making our system more efficient. So here we test the function by calling it twice with the same prompt. Tell me something about machine learning. So the first time, the system generates a new response because the prompt is not yet stored in cache. And then the second time, the system retrieves the stored response from cache instead of generating it again. This saves time and reduces API calls. Okay. Now let's look at this slide that shows us a visual representation of how retrieval augmented generation and cache augmented generation work. The top section is basically retrieval augmented generation, and that's what we're going to start with. So say this retrieval model receives queries, let's say query 1 or query 2. It's going to search for the relevant knowledge. It's going to search for the relevant knowledge in a pre-computed knowledge base, where it's going to get items such as K1 and K2. So this ensures that the model has the right context before passing the query to the large language model for processing. And so once this retrieval model has fetched all the relevant knowledge, it sends the query along with this knowledge to the large language model for processing, and the large language model will produce answers A1 and A2. So now this section here looks at cache augmented generation. So instead of relying on external data sources, the system could store the processed knowledge in a knowledge cache, as you can see here, to help optimize future queries. So each and every query, along with its corresponding knowledge, is first stored in the knowledge cache. For instance, when the first query Q1 is processed, its knowledge is cached, ensuring that if a familiar query comes in later, the system can retrieve information instantly rather than running a full retrieval again. Now, let's say a second query 2, arrives. Instead of fetching knowledge externally, the system first checks the cache to see if relevant knowledge is already stored. If Q1 is no longer needed, it is truncated to make room for Q2, as we can see here. This helps the cache memory to be efficient while ensuring quick access to the most relevant information. So by doing this, the model generates responses A1 and A2 quickly without any redundant retrieval steps. Thank you. So basically, this diagram highlights why cache augmented generation is a powerful alternative to retrieval augmented generation. Instead of performing real-time retrieval every time, cache augmented generation leverages pre-computed knowledge and caching, leading to significant efficiency improvements. This approach is faster, more reliable, and cost-effective when it comes to query handling and making it ideal for AI-powered applications. Thank you.
Hello to you all. My name is Ankunda Praise, and I'll be taking you through the rest of our presentation. Let's take a look at the key differences between cache-augmented generation, also known as CAG, versus retrieval augmented generation, known as RAG. CAG preloads knowledge directly into the model's context, making it faster since no retrieval is needed. It is also simpler as all required information is already available to the model. However, CAG is static and limited to preloaded data, meaning that it can't dynamically fetch new information. On the other hand, RAG retrieves external knowledge from a database, making it more dynamic and scalable. However, this comes at the cost of retrieval latency and the additional complexity of integrating external information. In summary, CAG is faster and simpler but limited, while RAG is more flexible, scalable but slower due to retrieval overhead. Choosing the right approach depends on the use case. Next, before diving into the benefits, let's quickly define what cache-augmented generation is. Instead of relying on real-time retrieval for external data, this approach stores and reuses relevant information from past queries, making AI models more efficient and responsive. Now let's explore the key benefits of this approach. Reduced latency. One of the biggest advantages of cache-augmented generation is that it eliminates the need for real-time retrieval, significantly reducing response time. Since the model can quickly access stored information instead of searching and retrieving data on demand, users experience faster and smoother interactions. Simplified architecture. Traditional retrieval-based systems require complex integrations with external knowledge bases, databases, or search engines. With cache-augmented generation, remove this extra layer, leading to a simpler, more streamlined architecture. This not only reduces development complexity, but also lowers maintenance costs, mitigates retrieval errors. Real-time retrieval systems are prone to errors such as retrieving outdated, irrelevant, or incorrect or even incorrect information. Cache-augmented by caching relevant data, cache-augmented generation ensures more consistent and reliable outputs, reducing the risks associated with unreliable external sources. To summarize, cache-augmented generation brings three key advantages: faster response times, a more efficient system design, and improved reliability. As AI applications continue to evolve, leveraging caching mechanisms can lead to better user experiences and more scalable solutions. Next, I'll be discussing some key challenges in cache-augmented generation, a technique used to enhance text generation by storing and retrieving past results. First, cache size management is a major concern. As the number of queries grows, the cache can become excessively large, leading to memory constraints and inefficiencies. Next, cache relevance plays a crucial role. Not all stored information remains useful over time. Irrelevant or outdated cache entries can degrade the quality of generated text. Additionally, cache expiration is a challenge, especially in real-time applications. Data stored in the cache can become obsolete, leading to outdated responses unless properly refreshed or discarded. Finally, the complexity of cache management cannot be ignored. Implementing an effective caching strategy requires sophisticated logic and balanced performance, relevance, and memory usage. Addressing these challenges is key to making cache-augmented generation more efficient and reliable. Now that we've discussed the challenges of cache-augmented generation, let's explore some of the solutions. First, implementing a cache eviction policy like recently used helps manage cache growth by removing old and infrequently accessed data, preventing memory overload. Second, using contextual relevance checks ensures that only useful and relevant data is stored, reducing noise and improving text generation quality. Next, having a cache expiration policy ensures that stored information is periodically validated, keeping the cache up to date and preventing outdated responses. Finally, leveraging machine learning models can help determine when cache data should be used, making the system more adaptive and efficient. By combining these strategies, we can optimize cache-augmented generation for better performance and reliability. Next, I'd like to introduce an advanced AI approach that enhances text generation hybrid models, which combine cache-augmented generation and retrieval-augmented generation. This hybrid approach leverages the strength of both methods to create more accurate, informative, and reliable responses. In AI-driven text generation, we have two primary techniques: Cache-Augmented Generation and Retrieval-Augmented Generation. Cache-Augmented Generation, basically this method stores and reuses previously generated content, reducing response time and eliminating the need for real-time retrieval. RAG, on the other hand, fetches relevant information from external knowledge sources in real time, enriching the model's responses with up-to-date facts. A hybrid model combines both of these, allowing AI to access both stored knowledge, that's cached content, and external sources, which are the retrieved documents when generating responses. Why is this beneficial? For starters, there are more accurate responses. By combining caching with retrieval, hybrid models ensure responses are not only fast but also factually accurate. Cache data provides efficiency while retrieval supplements it with the most relevant up-to-date information. This is particularly valuable in dynamic fields like news, finance, and research, where accuracy is crucial. More informative outputs. A system that relies only on cache responses may become outdated, while one that depends solely on retrieval may slow down due to processing delays. Hybrid models strike the perfect balance. They provide detailed, well-structured answers while maintaining efficiency. When a query can be answered from cache knowledge, the system responds instantly. When additional details are needed, the system pulls in new data. This adaptive approach leads to smarter, context-aware AI interactions. In summary, hybrid models offer the best of both cache-augmented and retrieval-augmented generation. They enhance AI-generated responses by making them faster, more accurate, and more informative. This powerful combination is shaping the future of AI by ensuring users receive reliable, context-rich, and up-to-date answers. Then finally, I'll be talking about Turbo RAG, how it works, and where it represents a major breakthrough in AI text generation. What is Turbo RAG? Turbo RAG is a novel RAG system built to enhance performance by reducing both computational overhead and time to first token latency. TTFT refers to the delay between when a user submits a query and when the AI model begins generating the first word of this response. Conventional RAG systems suffer from high TTFT because they must perform multiple steps in time, including retrieving relevant documents, processing and encoding them, computing key value caches dynamically. These processes take time, increasing response latency. Turbo RAG solves this problem through pre-computation. How does Turbo RAG work? Instead of computing key value caches in no time, Turbo RAG pre-computes and stores them offline. This means document chunks are processed in advance and their KV caches are stored. During inference, when the AI generates a response, it retrieves the pre-computed KV caches instantly, eliminating the need for online computation. The system can then pre-fill these KV caches during response generation, dramatically reducing response time. This method bypasses the need for real-time KV computation, making Turbo RAG significantly faster and more efficient than other conventional RAG models. Benefits of Turbo RAG. First, we have faster responses. One of the most impressive benefits of Turbo RAG is its ability to reduce time to first token latency by up to 9.4 times. This means that users get responses almost instantly, creating a much smoother and more engaging experience. Two is lower computational overhead. Since Turbo RAG pre-computes and stores KV's patches, the system requires fewer resources during online inference. This leads to reduced computational cost, lower power consumption, better scalability, allowing AI systems to handle more requests efficiently. It also maintains comparable accuracy. Despite the drastic speed improvements, Turbo RAG maintains the same level of accuracy as conventional RAG models. This means that you get faster responses without compromising quality. Turbo RAG represents a major step forward in optimizing retrieval-augmented generation. By pre-computing and storing KV caches, it achieves faster response times, reduced computational costs, and greater scalability while maintaining high accuracy. This breakthrough makes AI-powered systems more efficient, cost-effective, and user-friendly, setting the stage for the next generation of intelligent applications. That's all I had for you today. Thank you.